In this video, we will take a look at the big picture of what differential equations are good for. So any math, science, engineering field where you make an assumption that involves a rate of change, that rate of change statement can almost always amount to some sort of a derivative. Now, if you can find the function that satisfies that derivative statement, or in other words, solve the differential equation that arises from the assumption that you're making, then you can model a bunch of different situations that involve that same assumption. So if you look at what I've set up on this screen, we're going to be talking about exponential growth and decay. So being in calculus, you've probably seen the graph of e to the x a decent amount. What we're going to be doing here is we're going to be looking at a bunch of situations that e to the x parent graph can be used to model. So in biology, maybe algebra 2, you might have used exponential growth for population models. That works for like population of a bacterial culture, population of a city, of a country, of the planet. In chemistry, you definitely have done half-life problems. I don't know if you did them with exponential decay, but I'm guessing you for sure used logarithms when you dealt with your half-life problems. We're going to be using an exponential decay model in this section to try to look at some half-life scenarios. Any of the problems that I just identified that you maybe have seen in those other places in the past, they both make the same assumption. And the assumption is this: the rate of change of whatever quantity you're considering, so the rate of change of the population, the rate of change of the amount of the substance that's remaining, that's decaying, the rate of change of that quantity, it's directly proportional to the current level of the quantity. This statement that's here in red allows us to write this differential equation. So it's a differential equation because it's obviously an equation because of the equal sign, and it's got differential equations over here. It's an equation that is a derivative, essentially. So look at the beginning of this sentence. The rate of change of the quantity at hand. Well, that's the derivative of the quantity at hand. So the quantity at hand I'm calling y, and then the rate of change is going to be happening over time rather than with respect to x. So the rate of change of y with respect to t is, if something is something in math, it's equal to it. So the rate of change is directly proportional. So if something's directly proportional to something else, that means there's some constant of proportionality. And in this case, I'm using the letter k to represent that constant of proportionality. So the rate of change is directly proportional to the current level of the quantity. Well, if the rate of change of the quantity is dy dt, then the current level of the quantity is y. This statement gives us this derivative. If we can solve this differential equation, we then are going to have a solution that can be used to model anything that would make this assumption. Population growth, radioactive decay, even continuously compounded interest. You're constantly gaining value, so the rate of change of that account value is directly proportional to the current amount that's in that investment. So this is a problem from 7.1 of our textbook. 1 through 8 are all very similar to each other. They say find the solution of the given differential equation that satisfies the initial condition. So this is the differential equation that they give us. If you notice, it has the form of the differential equation we just looked at. The rate of change of the quantity at hand is proportional, so the constant of proportionality in this case is -2, to the current level of the quantity. And then what they provide us with here is they provide us with the fact that when we put 0 into this solution, we're going to get -6 back as the y value. So if we're going to go about solving this, we're going to go through the method of separation of variables, which basically means you want the y and the dy on the left side of the equal sign, and then you want the dx and the x's on the other side. So what I went ahead and did here was I divided the dy by y, right? The y was multiplying the -2, so the way that I would algebraically get that to appear on the other side would be to divide both sides by y, and then I multiplied both sides by the dx. This -2, you'll notice that I let it stay put. I didn't bring it across to the other side of the equal sign along with the y. And the reason for that is because what we eventually want is a y equals equation. The more stuff that we take to the left side of the equation with the y, the more stuff we're going to have to move back later on in the process. So a good habit to get into would be to kind of start to adopt that on your own too. Take as little as possible to the left, because you're eventually going to want to move stuff back to the right come some point later in the problem anyhow. So the way that I would get rid of my differentials, the way that I would undo my my dy and my dx, is by taking the antiderivative on both sides. So when I take the antiderivative of this side, ignore these e's for just a few seconds. When I take the antiderivative on this side, I get natural log of the absolute value of y. Now you might look at this and not really think that that's the case, but just bump that dy out of the fraction. It's 1 over y times dy. So we do get natural log of the absolute value of y on the left. On the right, I'm going to get negative 2 x to the first divided by 1 plus the constant. And like we talked about just a few seconds ago, if I add the constant here and I have another constant here, when I solve this for y, I'm going to bring this constant over to join this one, and they're going to combine into just some new constant I still don't know the value of. So to keep things nice and efficient, we're typically just going to add the constant on the side of the equation that includes the independent variable. Now, you'll notice I told you to ignore these base e's. What I've done is I've exponentiated on both sides of this equation because we would like to have y isolated. So if I'm trying to isolate y, I'm going to have to undo this logarithm. So I'm going to get that to happen by applying the process of exponentiation. Both sides become powers on a base e. On the next line, what you'll notice is I still have the absolute values. That's something that we're going to handle in a weird sort of way. This happens pretty frequently. A lot of differential equations that you're going to be solving with this method are going to end up with natural logs and the absolute values somewhere within them. So handling the absolute values appropriately is going to be discussed for the first time in the next few seconds. Hopefully this is something that you can latch onto pretty well. So look at this line right here. After I've applied that exponentiation process, canceled the natural log and the e on the left, still have absolute values. The reason why I still need absolute values on this line that I'm pointing at right now, look at the right side of the equation. E to a power is only ever going to be positive. You will never get a negative value no matter what power ends up here as the exponent on the base e. So because the right side of the equation is only able to be positive due to it being e to a power, the left side of the equation still has to have the absolute values there so that it is also only ever positive. Now what I did on this next line is kind of sneaky. Whenever we have addition in an exponent, we are able to re-express that as multiplication of like bases. So I'm sure you've gone from a line that looks like this to a line that looks like this a lot. If I do e to a power times e to a power, I'm going to have to add the powers in order to simplify that into one base e. In this case, I'm going the opposite direction down that street. I'm taking the addition in the power and I'm re-expressing it as multiplication of like bases. The benefit to this is what I'm going to talk about next. This right here, e to the c, this is a constant. 2.7 to a number is going to be a number. So what I'm doing is I'm re-representing this e to the c as a. Now notice I'm not claiming that e to the c is equal to a. I'm re-representing e to the c as an arbitrary constant a. The reason why it's significant to say that it's an arbitrary constant a and not to necessarily say that a is equal to e to the c is this. Look at this line right here. E to a power is positive times e to a power again, which is also positive. Right side of this equation is only ever able to be positive. Left side has to remain positive. Absolute values are still necessary there. When I re-express e to the c as an arbitrary constant a, think about the right side of this new line. This arbitrary constant, if I'm not demanding that it be equal to e to the c, if I'm just saying this is an arbitrary constant a, this a could be positive, this a could be negative. When I multiply that together with e to the negative 2x, I've given the right side of the equation a way to become negative, should a be negative. Therefore, I can give the left side of the equation a way to become negative as well, and I can drop the absolute values at that point in time. So I finished this up at the top of the next line on this screen. I guess before I move up there, this is the general solution. I don't know what that constant is. So this is the situation where every function of this form is going to have this as the derivative. But what's the specific function that has this derivative that goes through this ordered pair, 0, negative 6. So if I put negative 6 in place of the y, so I just took what was at the bottom of the screen here, and I put negative 6 in place of the y, and then I put 0, right? That was the x value, the input there. I put 0 in for x. E to the 0 is 1. A times 1 is A. That gives us an A value of negative 6. And this is the specific solution, or the particular solution, the one solution that has this derivative and goes through this ordered pair.